Okay, so continuing our discussion of evolutionary tree reconstruction. In this lecture, we are going to focus on distance based tree reconstruction algorithms. So in the last lecture, just to give a quick recap, we introduced what phylogeny trees are. So remember that here we are trying to infer the evolutionary relationship of given objects. So for example, you may have present day species and we want to infer how they evolved over time. That is, we want to infer the past evolutionary history of the present day species. This is best viewed as a tree like data structure, where if you keep going forward, you are inferring the ancestors, and the topmost node, that is the root of the tree, would indicate the common ancestor of all the species. We also looked at multiple applications of why building phylogeny trees is important. And finally, we looked at the properties of these trees, that is the difference between rooted and unrooted trees. What do we mean by edge weights? And we also looked at that the total number of distinct possible trees can be extremely large if you are given a number of leaf nodes. So that was the third point, was to emphasize that we cannot consider enumerating all possible trees while looking for an optimal tree for this problem. While I close the lecture by giving you an overview of the methods that exist. So one is the distance based methods, where we find a tree that fits the given pairwise distance information between taxa. The second was the maximum parsimony based methods, and third was maximum likelihood based methods. For this lecture, we are going to focus on distance based methods, and I am going to give more details of how distance based methods work for tree reconstruction. So let us get started. Now given a tree, so let us use this notation dij as the length of the path between leaves I and j. Then if I give you a tree with weighted edges, it is trivial to compute dij between any two leaves I and j. For example, if I consider leaves 1 and 2, then d1 comma 2 is trivially, you can see that it is equal to 12 plus 13 plus 12, that is 37. But in practice, that is not the problem that we face. So in practice, the biologists face the opposite problem, that is they are given an n cross n distance matrix D, where they know the pairwise distances between the leaf nodes, and they require the tree T which has n leaves and that is consistent with the distance matrix D. That is, they know the distance matrix, that is the pairwise distances between the leaf nodes, and they are looking for a tree which is consistent with that distance matrix. So it is an opposite problem, that is you have an estimate of the distances between all the leaf nodes, and you are looking for what kind of tree and what kind of edge weights you should set that is consistent with the matrix. So for example, in this particular example, you can see that this particular tree is consistent with the matrix shown. So for example, the matrix says that the distance between A and B should be 2, and this can be verified that yes, indeed the distance between leaf nodes A and B is 2. Similarly, you can check other values also. Now this is the problem that we would like to solve in general when we are considering distance based methods for tree reconstruction. Okay, so now one can ask, where do biologists get these distance matrices, right? So what do you think? Well, there are many ways, and for example, one way can be that you can consider pairwise edit distances of a common gene between all the species. So let us say you have a gene which is known to be conserved across all the species. You can consider the pairwise edit distances of the gene sequence and use those edit distances in your matrix, right. So that is one way. And suppose now, so using such methods they have a distance matrix, and from that distance matrix they want to infer a tree. Now again I have to remind you that when we are solving this problem, we have to identify the shape of the tree as well as edge weights. In the last lecture we already saw that the number of distinct trees grows very quickly with the number of leaf nodes. So not only you have to identify the tree shape out of many possible tree shapes, but also the edge weights on the tree. So given the large search space, you can appreciate that why this would be a challenging problem to solve. So to get started, let us start with some simple scenarios. Let us say that we have only 3 objects or 3 species that we are working with. Now when n equals 3, the good news is that we already know the tree shape, because there is only one tree shape that exists which has 3 leaf nodes. So there is only single unrooted tree shape with 3 leaf nodes, which is shown on the top. All we have to do is to compute the edge weights, right. So that is, we have to think about, so given the 3 objects we are interested in, all we need to do is to define the edge weights between the internal node and each of the 3 species. That is, we have to figure out D1 comma C, D2 comma C and D3 comma C. And obviously we are given as input that pairwise distance matrix. So we know the pairwise distances between these 3 objects or these 3 taxa. So we know the distances between D1 to 2, we know the distances between D2 to 3, and we know the distance between D1 and 3. So it is a simple linear equation problem, right. So all we have to do is to just set up the constraints, and because we know that D1C plus D2C would be equal to the distance between leaf node 1 and 2. Similarly, the D1C plus D3C would be equal to D13 and so on. So you have 3 equations and 3 unknowns. So these are your unknowns, and on the right hand side these values are known to you. So because it is a simple setup, you have 3 equations and 3 unknowns, it is very easy to find out the values of D1C, D2C and D3C in terms of the known values. So using this simple set of equations, you can figure out the edge weights, and as a result when n equals 3, this problem is easy to solve. Moving ahead, what about the general case? So again we are given now a pairwise distance matrix, and this time we have a n cross n matrix, right. So assuming you have n objects, you are given a n cross n matrix. Now remember, so even if there is an oracle which gives us the correct tree shape, so let us say we don't have to worry about figuring out the correct tree shape anymore. There is an oracle that comes and tells you the correct tree shape. Now even then, recall from the last lecture that an unrooted tree with n leaves has 2n minus 3 edges. We gave this argument in the last lecture. Now in this scenario, how many unknown variables do we have? Well, if there are 2n minus 3 edges, we have to set the weight of each of those edges. So clearly we have 2n minus 3 unknown variables that we have to solve for. How many constraints do we have to satisfy? Well, observe that we have to find a tree which is consistent with the given distance matrix. That is, we have to make sure that the distances between all pairs of leaf nodes are matching with the distances in the tree. So from this distance matrix, you have n choose 2 constraints, right. So because you have only 2n minus 3 variables and you have n choose 2 constraints, you can clearly see that this system of linear equations may not always have a solution, right. So it is not guaranteed that all such systems of linear equations will have a solution, because you have more constraints than the number of variables. So this motivates the definition of additive matrices. A matrix D containing pairwise distances between n objects is said to be additive if there exists a tree T which has the following 3 properties. The first property is that it must have at least n nodes, and n of its nodes should be labeled with the given n objects, right. So out of this tree you should have n labeled nodes which are labeled with the n objects respectively, right. Now this tree must have positive edge weights, and for every pair of labeled nodes I comma j, the length of path from I to j should be exactly dij. That is, it must be consistent with the given matrix. The path length between every pair of objects must be consistent with the given matrix D. And if there is a tree existing that satisfy all these 3 properties, then we can say that the given matrix D is additive. So on the bottom I am showing you an example of an additive matrix. Why is this additive matrix? Because there exists a tree which is consistent with this matrix. So this tree, for these 4 objects, this tree has 4 labeled nodes. It has positive edge weights, and if you consider every pair of labeled nodes I comma j, let us say we consider A and D, then the distance between AD is 4, which is consistent with the matrix D. So in this case we can say that this particular matrix is additive. Whereas here is one more example where the matrix is not additive. So for this particular matrix, it turns out that there is no tree which would satisfy or which would be consistent with the matrix. So this is a non-additive matrix. Now how do we solve? So let us say we assume that the given matrix is additive. How do we reconstruct trees from a given additive matrix? The first observation that might be useful is the following. So suppose again there is an oracle which tells us that there is a pair of neighboring leaves I and j in the tree which share a common parent node k. So that is, it has given us some information about the tree shape. It is telling us that you have leaves I and j as neighbors and they share a common parent node k. So these leaf nodes occur next to each other and they share a common parent node k as shown in the figure above. Now this information can be very useful for us. Why? Because as soon as we have this information, we can simplify our problem. This is how we can simplify our problem. So observe that if you consider any other leaf node m in the tree, so let me consider leaf node m, then observe that dim plus djm, that is I am adding up the distances between dim as well as djm. This is equivalent to 2 times dkm, because observe that I am traversing the path between k and m twice, and I can subtract the distances between I and k as well as j and k. So this is trivial to see from the figure as well, that this equation should be universally true for every leaf node m, which means that if this is true, then I can compute dkm in the following way. So I can compute dkm in terms of dim, djm and dij. All of these 3 values are available in the matrix D, because these are pairwise distances between the leaf nodes. Now why this helps is because what we can do is we can replace the 2 I and j nodes in the matrix with a new leaf node k. So we can assume that instead of having I and j as leaf nodes, we can remove I and j and assume k to be a leaf node, and we can update the distances of node k with every other leaf node using this formula. By doing this, what we have achieved is we have reduced the dimension of the matrix by 1, and as a result we have a simpler problem to solve. That is, we had the input of n cross n originally, and by removing 2 leaf nodes and adding 1 node, we have a slightly simpler problem to solve, in which the matrix has only dimension n minus 1 cross n minus 1. So now you can imagine that if I keep on applying this reduction, so if the oracle keeps on helping me by telling the pair of neighboring leaf nodes, and if I keep reducing the dimension of the matrix 1 by 1, then ultimately I will end up with a, let us say, a 2 cross 2 matrix, which is very trivial to solve. So for a 2 cross 2 matrix, all I have is two nodes, and I have to just connect them with the edge, right. So a 2 cross 2 matrix will basically look like maybe like this, and all I have to do is to have 2 nodes connected by a edge weight 3. So by reducing the dimension of the matrix 1 by 1, we have a simpler problem to solve, and then we can continue to expand and reconstruct the original tree with n leaves, right. So, once we have solved the simpler problem, we can bring back I and j, because we know that I and j are neighboring leaves, and we can easily identify the edge weights of these two nodes based on the given information. So, that is the intuition of how we are going to work, and let me formalize this idea in the next few slides. Right. So, keep reducing either until you have 3 cross 3 matrix or until you have 2 cross 2 matrix, because both 3 cross 3 and 2 cross 2 are trivial to solve, right, and we can compute and then expand the tree. Now, of course, the key challenge here is that we are assuming that there is an oracle which is telling us what neighboring leaves are, but finding neighboring leaves is non-trivial in general. Now, you may think maybe why is this challenging, like why should be finding neighboring leaves challenging, right? Because maybe we can just look for 2 closest leaves in the matrix, and maybe that should be neighbors in the tree, right, which is fairly intuitive, because the 2 objects which have shortest or minimum distance between them should be located next to each other in the tree. But unfortunately, that is not always true. So, here is a counter example shown here. If you think of the closest nodes here in terms of the pairwise distances, you will find that B and C have the lowest pairwise distance among all pairs. So, the lowest or the minimum pairwise distance is between B and C, but you can easily see that B and C are not neighboring leaves, that is, they do not share a common parent vertex. So, as a result, this intuition is unfortunately wrong, and we have to be careful in how do we identify the neighboring leaves. This challenge was addressed in 1987 by an ingenious algorithm developed by Saito and Nye. This algorithm is known as neighbor-joining algorithm, and this is the most widely used distance based method for tree reconstruction. This algorithm produces an unrooted tree. The key idea in this algorithm is to consider average distances of each node to every other leaf node when we are identifying neighboring leaves. So, instead of being greedy and looking for the minimum pairwise distance, it looks for it computes the average distances with all other leaf nodes while figuring out the neighboring leaves. Let us see how it works. So, again remember that we are given pairwise distances. So, this information is available to us. So, this is the n cross n matrix that we are given. The step 1 of this algorithm is for each taxa I will compute the average separation from all other taxa. So, let us say for taxa I, that would be basically the summation of all the distances of I to all other leaf nodes, and I will compute the average by dividing it by n minus 2. Now, why exactly is this n minus 2? That detail is unfortunately outside the scope of this course. For that you will have to refer to the original paper, but intuitively you are calculating the average separation or average distance of taxa I from all the leaf nodes. The step 2 of this algorithm is to identify which leaf nodes to merge. So, here we identify the pair of taxa that are close to each other, but also far from others. That is, we will identify a pair with minimum Dij minus Ri plus Rj. That is, we want them to be close to each other, but we also want them to be far from the remaining leaf nodes. And that is the key difference between the previous intuition that we had and the algorithm that this procedure is using. So, here we look for the leaf nodes which have minimum distance with each other, but also consider the average separation of the leaf nodes from all other nodes. Now, once we identify this pair I j, then our life is easier. All we have to do is to merge I and j with a new taxa u. So, basically we are merging I and j and we are replacing it with a new taxa u in the matrix D. We know the value of SIU from this equation. So, we use this equation to set the value of edge weight I to u, and the edge weight of edge ju will be set according to this equation. So, after this we can forget about these two nodes and consider u as the new taxa that is inside the matrix D. That is, we have reduced the dimension of the matrix by 1, and as we discussed before, we can initialize the distances of u to every other leaf node using the equation given here, right. So, this is the same equation that I showed you here, that is, if you know the pair of leaf nodes which can be merged, then you can remove those two leaf nodes and replace it with their parent node in the matrix D. That is exactly what we are doing in this step. We are replacing I and j with a new taxa u, and we can use this equation to compute the distance of u to every other taxa. So, we will revise matrix D based on this equation, and now at this step the dimension of this matrix D has reduced by 1. So, if now the final step is simple, that is, if you have more than 2 taxa remaining, then we have to repeat this process, that is, we update n to n minus 1 and then we move back to step 1 and repeat. That is, we again find 2 closest neighboring leaf nodes. So, we find the appropriate leaf nodes that should be merged, and again we keep repeating this merging process until we have only 2 taxa remaining, because once you have 2 taxa remaining, all we have to do is to just connect them with the edge. Let me show you a visualization of how this algorithm is working. So, this figure is taken from Wikipedia. Imagine you have 7 taxa that you are working with. So, you initially have a 7 cross 7 matrix. Think of each taxa as a leaf node, right, and you have the pairwise distances between all these leaf nodes. The neighbor joining algorithm will find the 2 leaf nodes that should be merged, that is, the 2 leaf nodes that are neighboring in the optimal tree. So, let us say it identifies f and g, then it will replace f and g with a new taxa u, and the distance matrix will be revised, the dimension will be reduced by 1. In the next step, C, again from now that we have u, again we will find out the pair of leaf nodes that are adjacent in the optimal tree. This time the algorithm has identified E and U that should be merged, and it merges it with the vertex or taxa V. Again it repeats the process. So, now it identifies C and D as the leaf nodes that should be merged. Finally, it continues and it computes the final tree that is consistent with the given matrix D. For a detailed running example, that is how the distance matrix D is getting updated, you can refer to the Wikipedia page. So, it explains this in more detail, but I hope the general intuition is clear. Now, this algorithm is guaranteed to return correct tree if you give it a matrix which is additive. So, if the matrix is additive, then it will give you the correct tree which is consistent with the matrix. However, what if your matrix is non-additive, which happens commonly in practice as well? In that case also you can use the neighbor joining algorithm and still obtain a tree which can be a close approximation to the optimal tree. So, basically neighbor joining algorithm can be used as a heuristic in practice for non-additive matrices as well. Now, one known limitation of neighbor joining algorithm is that it can also return trees with negative edge weights, and that is one known limitation of neighbor joining, but otherwise this algorithm works very well in practice. Now, I hope with this lecture you understand how distance based algorithms work for tree reconstruction. That is, we are looking for a tree that fits the given pairwise distance matrix between the taxa. In the next lecture, we will look at the maximum parsimony methods, which is another class of methods for tree reconstruction. Thank you.